Hello everyone. Today we will discuss about adder in digital electronics. Before we are going to discuss adder, let's talk about what is combinational circuit and is the adder is also a combinational circuit. So what is combinational circuit? Combinational circuit is those circuit which does not have any memory. What is memory? Memory actually a storage unit, just like flip-flop, which we are going to discuss later. So, a combinational circuit does not have any memory. So, why memory is affected any circuit? Because if you have a memory, you can store some data on it, and if you does not have that memory, then you cannot store any data. So, at any moment of time, if you have some input, you are getting output on the basis of the input at that time, not any previous output or any previous input. So you already understand what is the importance of memory. If you have a memory, then there may be output affected by the previous output or the previous input, which is stored in the memory. And also in combinational circuits, there are n input and m output variables. Here n may be greater than or equals to m, less than equals to m, or greater than m, less than m. And now we are going to discuss, is adder is a combinational circuit? The answer is yes, because the adder does not have any memory unit, and any instant of time the output is directly dependent on the input at that moment, and it also holds n number of inputs and m number of outputs, where n is less than m. So here we can conclude that the adder is a combinational circuit. Now, who invented this adder? George Stevens invented the 2-bit binary adder in 1937. This is just for your information. Now, we are starting with the half adder. Actually, there are two types of adder. There are many types of adder, but we are only going to discuss the half adder and then full adder, and a few names other which is actually handle the multi-bit adder. Okay, now before we are going to discuss the half adder, let's discuss about some addition rules. Here you can see that if we add 0 and another 0, the sum will be 0. And similarly, if we add 1 with 0, then the sum will be 1. And if we add 0 with 1, again the sum will be 1. But if we add 1 with 1, then the result will be 1 and 0. I hope you all already know how to add. So here you can see this extra 1 is called the carry. Okay, so this is our basic rules of sum. Now we are going to create the truth table. So here we have two inputs A and B, and output C for carry and S for sum. Now if we have two inputs or 2 bits, then the possible cases are 4, 2 to the power 2, which is 4. So we already create 4 possible combination: 0 0, 0 1, 1 0 and 1 1. And by following these rules, we are performing the sum. So here 0 0 means both are going to be 0. 0 1 means sum is 1, but there is no carry, so carry is 0. Similarly, 1 0 means sum is 1, carry is 0. And if we add 1 1, then we already discussed here, the sum is 0 but the carry is 1. So we already know the rules. So we are writing carry is 1 and sum is 0. Now, if we use the Boolean rules or Boolean postulates, then we can solve what is the expression for S, that is sum, and what is the expression for C out, that is our carry out. Now S equals to, you can see here we have 1. That means what? That means in our input we can see that A is 0 and B is 1. That means A bar B, which we are writing here. Similarly, for this one, in input we are seeing that A is 1 and B is 0. So the output is so our expression is A B bar, and we already know A bar B plus A B bar actually represents A XOR B. So our sum is A XOR B. Similarly, for carry, in our carry column, we are seeing that we are notice that a single 1 is present, and for this one in input we are getting A equals to 1, B equals to 1. So our expression will be C equals to A, B. Next, we are going to draw the circuit for this expression. So remember our expression sum equals to A XOR B and carry equals to AB. Here we already write the expression again. Here the circuit, you can see that A and B is our input, and in output for sum it is A XOR B, and for carry it is A and B. This is a very simple circuit. I hope there is no complications, and this is as per your observations that if we have 1 1, then what will be the output? Output will be 0 1. 1 is the carry and sum is 0, and when it is 0 0, you already know both are going to be 0 because sum of 0 0 is 0 sum and carry is 0. Okay, next we are going to discuss if we implement this half adder by using a NAND gate, then how it will looks. The circuit will be looks like this. Here you can see A and B are input. So after gate 1 it is AB bar, and after this gate it will be A into AB bar, then again whole bar, because here we already have AB bar which is go through this line, and from here A is coming. So A and the result AB bar is again going through this NAND gate and have A bar. Similarly, for this NAND gate, we already have A B bar, and the input B is also coming through this NAND gate. So B into AB bar whole bar. And for this NAND gate, you can see it actually passes through the A into AB bar whole bar and B into AB bar whole bar. So we are writing here, after passing through this NAND gate, the output will be A, AB bar, B, AB bar. This is a single bar, this is a single bar, and this is a whole bar. I am not solving this here, but if you solve this expression, you can easily get that this is equivalent to A XOR B. And similarly, for this NAND gate, this is actually for our carry. So we already know our carry is AB. So here we have AB bar, which is passing through this NAND gate, and AB bar double bar. And we already know that by the Boolean postulates, if A bar of bar, which is equivalent to A, so this is equivalent to AB. So we already get our desired results as sum equals to A XOR B and carry equals to AB. So this is our NAND gate representation of half adder. Now we are going to discuss the full adder. We already know the rule for sum, but here a special case is arise which I am discussing in this side. Here we have in the full adder 3-bit input is there, A, B and C in. Actually C in means if there is any carry from AB which will be added in the next stage. That's why it is C in, and the actual carry output is C out, and this S is representing the sum. Now how it will perform? In full adder, first we are going to add A and B, and then with the result of A and B we are going to add C in, and the total result will be written in sum and C out. Okay, now let's move. First add A and B, which is 0 plus 0, which is actually sum equals to 0, carry equals to 0. Now with the result of sum we are going to add C in. So we have already sum equals to 0, adding C in, that means 0, results 0 for sum and carry. I hope you understand. Let's discuss the another example. Okay, so first add A and B. Now 0 plus 0, which is represents 0 for sum and carry. Okay, now we have 0 for sum, but we have to add another 1 with the results. So 0 we already have in our hand, and add with 1 actually results 1 for sum and 0 for carry. Okay, I think it's clear now. Again, if we add 0 plus 1, we already have 1 sum, but carry is 0. Again, sum is 1. Now we are adding 1 with 0. Then result will be unchanged. Sum is again 1 and carry will be 0. In the same way, if we add the next step 0 plus 1, then 0 plus 1, what will be the result? It results sum equals to 1 but carry equals to 0. Now what we said already? We said the C in will be added with sum. So we already have sum equals to 1 and C in equals to 1. So 1 plus 1 will represent 1 for carry and 0 for sum. Is it clear? Because we have 1 1, we already see in half adder that if we add 1 1, then 1 carry will arise. That's why we are writing 1 in the carry field and 0 for sum. If you recall, I already told if we add 0 and 1, then we already have sum equals to 1. But when we add sum again with C in, then it will change to 0 and carry will be 1. If you follow the same rules, you can see that 1 plus 0, which is 1 for sum, and 1 plus 0, again sum will be unchanged to 1 and carry will be 0. Similar way, 1 plus 0, sum will be 1, carry will be 0. But when again C in equals to 1 here, so we are adding 1 sum for sum and 1 for C in. So 1 plus 1 will represent 0 for sum and 1 for carry. Similar here, 1 plus 1 will represent 1 carry and 0 for sum. Again, in sum we have 0. and we have to add C in, which is already 0. So 0 plus 0 will represent 0 in sum field and carry will be unchanged. And for our final state, we are seeing that there are 3 ones. So if we add 2 ones here, look, if we add 2 ones, then we have 1 as carry and 0 for sum. Now, this 0 will be added with the third one. Then the result will be 1. Here in our first addition, we see that we have a carry. So this one is our carry. And in our next addition, we are seeing that there is a 1 for sum. So this one is for sum. Okay. Okay. Next, if we solve this sum and carry out, we are getting those expression. I am not going to discuss the whole solution because it is already discussed in Boolean postulates. Here, if you solve sum, you will get A XOR B XOR C, and if we solve the C out, which is carry, we are going to get these results as AB plus C into A XOR B. Let's see how the circuit looks like. Here you can see our results for sum is A XOR B XOR C. Here A, B and C is our input. So in this gate we are going to input A and B and getting the result A XOR B, and in this gate we are taking input as C from here and the result of A XOR B from here. So the final output will be A XOR B XOR C, which is represent the sum. Now we have to implement the carry also. Here in our carry we see that the first expression is A and B. So we are taking A and B and passing through an AND gate is giving our desired result as A and B. Then the next expression is C into A XOR B. We already have A XOR B here. So we are taking the result as A XOR B and we are taking C from here and passing through an AND gate give us the desired result as C into A XOR B. Now we can see that these two results are added here. So we are passing through these two outputs through an OR gate and we are getting A into B plus C into A XOR B as our desired output for carry. Okay, this is for your general representation how it executes. So this is our actually full adder circuit. Here you can see that in our half adder there are a single or XOR gate and a single AND gate. But in our full adder there are two XOR gate and two AND gate and an extra OR gate. So we can say that a full adder is consist with two half adder because an XOR gate and a AND gate is representing a half adder. So if we consider this XOR gate and this AND gate a single half adder and this second XOR gate and this second AND gate another half adder, then we can say that two half adder is consist with an OR gate representing a full adder. Now This is the NAND gate representation of this full adder. I hope by following the similar process we already discussed in our previous half adder representation, you can get the similar expression here. And this is your NOR gate representation for full adder. And this is your block diagram. If you want to simply writing any answers by using any block diagram, then you can use this block diagram. This is your half adder where A and B is your input and carry and sum is your output. And this is your full adder block diagram where A, B and C in the input and sum and carry is output. In our first slides, we already discussed that there are many adder which handle multiple bits, and those are some of examples like ripple carry adder and carry look ahead adder. These are going to we are going to discuss this topic in later classes. Again, thank you for your time.